very glad to announce our next speaker, who is Professor Egon Schulte, Professor of Mathematics, Northeastern University, Boston. First of all, I would like to mention he is one of the organizers of this nice conference. More closely, he organized the session on polyhedral symmetries, and I may say that this session was very fruitful, held yesterday. Egon, thank you very much for organizing and heading this session. I would like also to mention that he is author of numerous articles and papers on convex combinatorial and discrete geometry and some many related topics. And perhaps he is mostly known for his monograph on abstract regular polytopes. This is a mathematical theory in which the key, the central idea is the Coxeter groups. The Coxeter groups are, informally speaking, are the symmetry groups of mathematical kaleidoscopes. The title of his lecture is Skeletal, Polyhedral Geometry and Symmetry. Egon, please.
Thank you, Herr Provost. Everybody hear me? Okay? Okay. Yeah. So first of all, thank you, Gabo, for the kind introduction. And I'd also like to thank the organizers for actually inviting me to give a lecture. Gabo gave me a little more credit than I deserve. I'm not technically an organizer of the meeting, of the session. But in any case, thank you. So I'd like to talk about a very old subject, which sort of lies at the heart of symmetry, polyhedral, and polyhedral structure in Euclidean space. And as we all know, polyhedron have a very long history going back to the Greeks as far as the mathematical treatment is concerned, and as I said, closely tied to symmetry. And with the passage of time, if you look at over the last 2,500 years, there have been many changes in the point of view of what a polyhedron is. And there are many different definitions. In fact, if I ask you to give me a definition of a polyhedron, then I would probably see a lot of very different definitions. So here at the bottom you see some pictures that you might want to call a polyhedron. Here, for example, the icosahedron, we have seen that many times. Then here is one of the Kepler poles. So polyhedron, well, that's already a little more of a stretch to call that a polyhedron because it has star-shaped faces. And then these two structures are finite objects. But if we also allow infinite objects, then suddenly there are more polyhedrons. So one of these Petri-Coxeter polyhedrons. And as you move to the fourth one, that's even more of a stretch. This is just a local picture of a polyhedron that has no longer flat faces. And here, this object, that looks like an imposition on the audience to call that a polyhedron initially, but we will see that it makes sense to call this a polyhedron. But let me start in a more rigorous way. The Platonic solids were sort of the most famous polyhedra, and they were also the ones that were initially called the regular polyhedra in Euclidean space. And what is the emphasis there? The emphasis is on the solid. Yeah, so we view polyhedron as a solid. And here we see the icosahedron, and throughout the talk I will be using symbols consisting of two numbers. The symbol is called the Schläfli symbol, named after Schläfli, who in the 1950s or so, 1850s, sorry, made a lot of contributions to the theory of regular polytopes in higher dimensions. And in any case, that's called the Schläfli symbol, and it has two entries. The first is a 3 that tells you that the faces are triangles, and the last is a 5, and it tells you that the vertex structure is a pentagon. So there's the 5 Platonic solids, and they are the regular polyhedra in ordinary Euclidean space. Until about 1600, when Kepler found two more, and another 200 years later, Poinsot found 2 more. And so what's different here? They are no longer solids. So I don't want you to look at these structures as solids. They are made up, for example, the one on the left, it's made up from 12 pentagrams. And here, I trace one pentagram for you. So here, top, go here, we go here, we go here, we go here, we go here. So it's a pentagram, so it's a system of 12 pentagrams that all fit together nicely in a polyhedron-like fashion. But it's not a solid. And the same story is true here. And they were, again, regular polyhedra. They are just not convex polyhedra. And it was Cauchy who actually proved that these 9 polyhedra are the only regular polyhedra, which are convex or star-shaped. Well, until 1930s, when Petrie and Coxeter discovered 3 more polyhedra, which were regular polyhedra. And so what is different? What is different here? Well, the difference is here, they are first of all infinite polyhedra. So for example here, this is a polyhedron. It's really a polyhedral surface in 3-dimensional space. Yeah, this is just a patch of that polyhedron. Yeah, so it actually extends throughout space. And the surface of the polyhedron is actually decomposed or splits into hexagons. And you will see this here. These are the hexagons. And at each vertex you have 4 such hexagons coming together. And so what is different here also is that the vertex structure, the locus structure, is no longer captured by a planar object. So for example, let's focus here on this vertex here. And look at the adjacent vertices of that particular vertex. As you move around the chosen vertex here, you go down, you go up, you go down, you go up. So it's actually a skew square that captures the locus structure at the vertex. And so the vertex figure, that is actually called the vertex figure, the polygon that connects the adjacent vertices in the same way in which they surround the chosen vertex. Yeah. So that's the vertex figure is a skew square, actually. And that makes these figures possible. So there are 3 of them. So at the end of the 1930s, there were 12 regular polyhedra. Well, you might wonder, is that all? And you go on. And then in the 1970s, Branko Grünbaum changed the picture again. And the main difference, or the main point, was to restore the symmetry of the original definition of a polyhedron. We haven't given that definition yet, but I will. So what's the difference here? His idea was to rid the theory of the psychologically motivated block that membranes must be spanning the faces. So he considered structures where he no longer thought of a face as being a membrane that actually spanning some polygon. So so no longer the membrane is no longer the focus. It's just a cycle of a face that's the focus. And that's a very graph theoretical approach to polyhedra, and that proved very fruitful actually, and very powerful also. And then the question is, what are sort of the analogs of the Platonic solids among these kind of polyhedra? And the answer is the Grünbaum dress polyhedra. And I will show you more about the Grünbaum dress polyhedra in a minute. And if you think that from a mathematical perspective this is a stretch to actually throw out the membranes, then I can assure you that actually it's the right approach to polyhedra for the very simple reason, especially if it comes to symmetry, so that whenever you study symmetry as a geometric object, say, but there's also an algebraic object, namely the group of all symmetries, all isometries that preserves the object. And if you want to have 2 structures which are sort of categorically equivalent, that means nice class of geometric structures on one hand and the nice class of algebraic objects on the other hand, you want them to correspond to each other, then you have to go away from this membrane approach to polyhedron. But I make this more precise. So here, as I said, no longer membranes occurring in the face. So for example, the icosahedron is just viewed as consisting of vertices, edges, and the 3 cycles, which sort of correspond to the faces. So what type of polygons can actually occur as faces? So in principle, they could be convex polygons, pentagons, for example. We have seen pentagrams in the Kepler-Poisson polyhedron. Here's another star polygon. But you could also have skew hexagons, for example. So let me show you a skew hexagon. So I take here a triangular antiprism, and here on the mantle of it, I see a skew hexagon. I'm tracing it for you. That's a skew hexagon. So it's just a 6 cycle consisting of 6 vertices and 6 sides. And here, for example, is a skew 12gon. Yeah, so again, a hexagonal antiprism, and I trace the polygon that sort of surrounds the mantle. But that's not all. So in order to really sort of create a closed theory, you must also allow infinite faces. That's a little bit of a stretch. You are not used to it initially. And so for example, this, but extended to the left and right, would also be a face. It's a polygon, yeah, so a zigzag polygon that lies in the plane that could actually show up as a face of a polyhedron. And here, a helical polygon. So a helical polygon that can show up as a face of a polyhedron. So I think it's a good point now to actually give a formal definition of what a polyhedron should be. So a polyhedron P in Euclidean 3 space, so in ordinary space, is a finite or infinite family of simple polygons. Yeah, of the type that I showed you, called faces. We call these polygon faces, such that four conditions hold. And these conditions are sort of very analogous to convex polyhedron properties. And the first one, each edge of face is an edge of just one other face. Yeah, so if you have a convex polyhedron and you have a face of a polyhedron, then the edge lies in just one other face. So that's a reasonable condition to require. Then all faces incident with the vertex form one circuit. So there is a way of actually sort of moving around a vertex in much a similar way as in the convex case. Then the whole structure is connected in a nice sense. And finally, a discreteness assumption. You want that each compact set meets only finitely many faces, which simply means is that there are no accumulation points. So everything is sort of distributed nicely. No accumulation points. So this is a polyhedron. So this defines the type of structures which we would call polyhedra. And everything that you can that I've described before is actually polyhedron of this type. And then we want to study so initially at least, the analogs of the Platonic solids. It's the most symmetric polyhedra. And we will call them a regular polyhedron. Polyhedron is regular if its symmetry group is transitive on the flag. So I have to explain this. So a flag is a triple that consists of a vertex, an edge that contains a vertex, and a face that contains the vertex and the edge. That's called a flag in this context. And what you want is a property that the polyhedron looks alike at all flags. So in other words, at all comparable places, the polyhedron looks alike. So that's the highest symmetry you can get with polyhedron. Yes, you cannot get more symmetry. And we want to call these structures regular. And we will also be discussing later chiral polyhedra. And they are almost have this maximal symmetry that I mentioned, but a little less. They sort of exhibit chirality, and I will explain that when we get to it. And there are other classes, uniform polyhedra, so the analogs of the Archimedean solids and things of this kind. So let me give you an example of a polyhedron according to this definition. That's the so-called Petri dual of a cube. So I start with an ordinary cube. Has 8 vertices, has 12 edges, but I forget about the 6 square faces. So I throw out the 6 square faces. And I replace the faces by 6 cycles, polygons that are hexagons, and they are obtained as follows. So we will have 4 new faces which are actually hexagons. And the new faces that I pick are the so-called Petri polygons. And here, for example, the red Petri polygon runs like this. This cube polygon that runs on the graph of the cube. And for example, then there are 3 more such hexagons. Then the green hexagon, this cube polygon, runs on the boundary of the cube, the blue one, and the black one. And the formal definition of a Petri polygon is that any 2 consecutive edges lie in a face, but never 3 consecutive edges lie in a face. So once you have done going up here, you cannot go here because then 3 are in the face, so you must go here. Yes, that's the formal definition. So, in other words, by starting from a cube, 3-dimensional cube, and throwing out the square faces and replacing these faces by hexagons of this kind, we create a new object which is called the Petri dual of the cube, and that's a polyhedron according to our definition. It has 4 hexagonal faces. But let me also give you an example of a polyhedron that has helical faces. And I will have to do a little hand waving. So at the bottom you see here, so focus on the left picture initially. At the bottom you see sort of a square grid. Actually here on this floor there's a square grid. Yeah, so square tessellation. And over 1/4 of the squares I erect towers. And the towers are sort of are here just for reference. Oh, I should put this down here. The towers are there for reference, and we will use them to construct the helices. And you see every 1/4 of these bottom square tessellation is sort of used to construct these towers. And in these towers, I walk up one step at a time. Yeah? So for example, here I walk around this tower, going up one story at a time. And I do that in each tower. But I want to be able to come from every tower to every adjacent tower, so I build bridges, maybe these little bridges. So in other words, the towers must be sort of positioned, or the helices must be positioned in the right way to be able to construct these towers, these bridges. So at this point, once we have completed this picture, we have all the vertices and edges, and 1/3 of all the faces, helical faces, of that polyhedron. And now there are 2 more sets of helices, and they run from the front to the back. Yeah, so we go from the front to the back, in just the same way in which these go up. And they go from the right to the left, these green ones, the same way these go up. So there are three of these families. They all fit together nicely to give a helix-faced regular polyhedron. So it's a pretty complicated structure. And here you sort of see the top view from the top. From the top. If you sort of look from the top of the tower, then you see the blue thing, and you see the green helices as you project them down. You see the red helices as you project them down. So that was an example that had helical faces. Let me also give you a polyhedron that has zigzag faces. Okay, so what I do is I start with a square tessellation of the plane here on the floor, square tessellation, and I again omit all the squares of the square tessellation, as we did with the cube. And now I use again Petri polygons. And I follow the definition of the Petri polygons. That means any two but no three edges are in a face. So how would that be, for example, for the yellow Petri polygon? Horizontal, vertical, horizontal, vertical, horizontal, vertical. So as we continue, this would be an infinite zigzag in the plane, and that would be one face of the polyhedron. And there are lots of these Petri polygons, and if you take them all together, it would be a polyhedron. And that actually lies in it. So these are examples, but how do you actually go about enumerating them and actually proving that there are exactly so and so many? And that has to do with the symmetry group of the structure. You have to, in other words, you look at all the isometries of the Euclidean space that map the structure onto itself. And that turns out to have a very nice set of generators. That means it is generated by reflections. So it's something called a reflection group. And the reflection in classical polyhedral geometry, you would see that the reflections tend to be plane reflections. So reflections in plane, the geometric operation of reflecting in a plane. That would sort of be classical polyhedral geometry. In the skeletal context, you have to allow reflections in planes. You must also allow reflections in lines, which effectively means we're taking half-turns. Reflection in lines are half-turns. And you must also allow reflection in points, which are inversions. So the groups of these structures are generated by three reflections in each case, which can be plane reflections, they can be half-turns, or they can be point reflections. And then it actually turns out that after a long time, you can enumerate them. And here is the classification of these Grünbaum dress polyhedra that I mentioned. So the true number is 48, so not 5 as a Platonic solids, not 9 if you include the Kepler-Ponceau, not 12 if you also include Petri-Coxeter. So the truth is 48. And let me sort of roughly break down how this classification would work and show you some more examples. So first of all, it turns out there are exactly 18 finite structures which are regular polyhedra. So finitely many faces. And they are the 5 Platonic solids. There are the 4 Kepler-Ponceau polyhedra, so the 9 classical objects. And they're Petri duals. Yeah, so if I perform this Petri dual operation that I mentioned before on the Platonic solids and the Kepler-Ponceaus, then I create the other 9 objects. Okay, I showed you the Petri dual of the cube. And Petri dual, the operation again is to throw out the original faces of the polyhedron and to replace them by the Petri polygons of the polyhedron. Yeah, so we have 9 plus 9 finite objects. So there are 18 finite objects. Then there are 30 infinite objects. And we call them a pyrohedron. And they break down into 3 groups. So the ones that actually live in a plane, there are 6 of them, and 2 classes of 12 objects. And so the plane ones are relatively simple to describe. They are just these regular tessellations of the plane, the ordinary regular tessellations of the plane, plus the Petri duals. Yeah, so we have the ordinary regular tessellation, other tessellation by square, triangle, and hexagon. So if we again omit the actual, say, squares, and take the Petri operation, we get again 3 new ones, and they are altogether the 6 planar polyhedra. And then there are 2 classes of 12s, and the first class of 12s is essentially built from the planar ones. And they are what we call blends. And what you do is you take one of the 6 planar objects and you blend them with the 2 possible regular regular polyhedra, if you want, on a line. And what are sort of the regular one-dimensional polyhedra? They are a line segment or a tessellation of a line by unit intervals, say. So for example, what that means is if I take this structure here, that's obtained as follows. I take 2 square tessellations, here the bottom one and the top one, parallel to that. And what I do is I build a new structure that's obtained by starting here at the vertex and replacing, say, the bottom square here on the left by a skew square. Then I go from here to the top vertex and down to the bottom vertex, top vertex. Yeah, so I alternately join the edges, join the vertices, and I create in this way sort of a roof-like construction, if I want. And that would be one example of this square tessellation blended with a line segment. Now, if I take the square tessellation and blend it with the linear tessellation, so to speak, with a tessellation of a line by unit intervals, then what I'm effectively doing is I'm taking the squares of the tessellation and I'm sort of let them rise as helices. Yeah, so over each square of the original tessellation is a helix rising, and adjacent, if I take adjacent squares, the helices rise in an opposite orientation. And here you see this, for example, you have these 4 columns, and over each square at the bottom there's a helix rising. But with this one, it's a red helix. Yeah, so it continues, of course, infinitely. So these structures have the property, if you project them down onto the base plane, you recover one of the 6 planar objects, and if you project them, say, horizontally, then you recover one of the linear objects. So there are 2 times 6 reducible polyhedra. And then there remain the irreducible polyhedra. That's considerably more complicated, actually, in general. So they can all be tabulated in a nice picture like this, which sort of summarizes some. So here I point out the Kepler the Petri-Coxeter polyhedra to you in this picture. Here at the top, these are the Petri-Coxeter polyhedra. You can do the Petri operation, that's pi, on them. Yes, and whenever you have a polyhedron, you can do the Petri operation. But there are other operations that you can also do. But rather than actually focusing on sort of theoretical part, let me show you another picture. So for example, this is the PT Coxeter polyhedron that I had initially, that consisted of hexagons. Yeah, so that the structure had is of type 6-4. So 6 hexagons, 4 at a vertex. That was the example that I had. And now what I do is I preserve my vertices and edges and throw out the hexagons. And now I replace these hexagons by the Petri polygons, by all Petri polygons. So for example, here's a green one. It's like this. Yeah, so it goes up in spirals. It's a helix actually. And the blue one, that's here. And again in spirals. And the red one. And the yellow one. Yeah, so that's a Petri dual of the Petri Coxeter polygons. They all look like this. So not everything is a Petri, well, everything is a Petri dual of something else, but not of the Petri Coxeter. And one can actually look at the theory more extensively, but so the answer is there are 48 regular polyhedra. The classical ones, the 9 so Platonic solids, the Kepler-Poinsot polyhedra, then the Petri Coxeter polyhedra, and the 30 pyrohedra that I just mentioned. A lot more than one thought initially. So now the question is, to what extent are there chiral polyhedra? And so let me go back to Lord Kelvin and give you sort of his definition of a chiral polyhedra, of a chiral figure. I call any geometrical figure or group of points chiral and say that it has chirality if its image in a plane mirror, ideally realized, cannot be brought to coincide with itself. And so the word chiral comes from the Greek word chara, care, I guess I'm not sure I pronounce it correctly, which means hand, and here is sort of the illustration of this chirality. Namely, here you take the right hand, you take sort of the I take this line here and reflect the right hand over here, then it becomes the mirror image of it, which in effect is the left hand. And you cannot actually move in the plane the right hand by a direct symmetry onto the left hand. So in other words, we want to have this kind of phenomenon in this polyhedral context. And so what we want to do is we want to study chirality in the presence of otherwise maximal symmetry. So we want to have a symmetry that is as large as possible, but the structure should still exhibit chirality. So just a tiny bit down from the regular ones. And so here, the snap cube, the snap cube is a geometric figure that has chirality. Right? According to the definition that I just described, the snap cube, I think everybody has seen probably that picture, has a lot of symmetry. So what, the way this is obtained is you take a cube, place a little square into one of the square faces of the cube, twist it a little bit, then apply all rotational symmetry. And that gives you the snap cube. So very symmetric object, but it will not be symmetric enough for us because it, for example, it has two kinds of faces. We would not want that in our definition. So the formal definition would be this. There are two, remember, the definition of a regular polyhedron was that all the flags look alike. Yeah, so the flags, remember, was a triple consisting of a vertex, an edge, and a face. So at all comparable places, the polyhedron looks alike. And for a chiral polyhedron, you have sort of two prototype of places. There's one, the first type, and the second type that's connected so to speak. Yes, so for example, this would be a flag. I pointed out to you. This is my vertex, this is my edge, and this would be my face. But for example, if I take this flag here, I replace the original vertex by the one on the right, but take again the same edge, but this face, that would be in the chiral polyhedron, they are not equivalent. So there are two different prototypes of places. So we want maximal rotational symmetry, but no reflective symmetry. That's what it amounts to. And the rotational symmetry means not necessarily that the symmetry is actually given by a rotation. It could be a rotatory reflection, for example, that has the effect of moving the vertex, the vertices in a face. And so you start looking around for interesting examples, and then you observe there are no classical examples because we want to have the maximum symmetry and chirality at the same time. There are no classical examples. There are no convex polyhedra that are chiral. There are no finite polyhedra that are chiral. And you can also not do this blended construction that I mentioned before. So, in other words, the examples that I discussed at the beginning, they are out. You have to construct them differently. And it turns down that there are chiral polyhedra. That wasn't clear at the beginning, if there are any chiral polyhedra at all, because we have this maximum symmetry. And the classification breaks down into two pieces, namely the one, in one class of objects we have polyhedra that have finite faces, and in the other class of objects we have polyhedra that have infinite faces, in fact helical faces. And so let me start with let me say some general facts about the chiral polyhedra that have finite faces. There are three very, very large families, so there are infinitely many to begin with, as many chiral polyhedra as there are rational numbers. And so, for example, in one class, the objects are of type 6,6. That means you have hexagons as faces, actually skew hexagons as faces, and you also have skew hexagons as vertex figures. And in these classes, if you, so all of these structures in this class, I'm focusing here on the right side, all of these structures, but two, are actually really chiral polyhedra, but there are also two objects that are regular, and suddenly, for two particular values of the parameters, the vertex figures as the faces become suddenly planar. And so it's a very interesting phenomenon. You have three very large families of chiral polyhedra, and in each class there are two regular ones where sort of exceptional positions for the parameters. And let me show you an example, or a local picture. That was actually on my second slide, if you remember this picture. And that is already an interesting example. So here, this is the neighborhood of a single vertex in one particular chiral polyhedron. And so here's my single vertex in the middle. And the vertex actually lies in 6 skew hexagons. So let me trace some for you. So here's the first hexagon. So I'm tracing the right one. It's actually a PG polygon of sort of a cube. Yeah, so the cubes are just there for reference. They're not part of the polyhedron. It's actually just the colored stuff that matters. So here's a red face, and on this edge sits another hexagon, maybe a green one. Then on this edge sits another one. Then I'm entering another skew hexagon. I just didn't have enough colors. Then here I have more, and so after 6 steps I'm returning to the original hexagon. And that's a local picture, so it extends throughout space in exactly that fashion. And here is another object in which the faces are not hexagons, but they are skew squares. And 6 coming together at a vertex. So here is a central vertex. And again, this is a neighborhood of a single vertex. The cubes are again there just for reference. And here there are 6 squares that surround that vertex. So let me trace a blue square. And on this edge sits a red square. On this edge sits a green square, then a blue square, a red square, and so on. So there are 6 squares that surround the vertex, and then it closes up. So the structure goes throughout space, and here is actually a physical model that was built by Daniel Pellicer, who is somewhere in the audience. And this was the last example that I just mentioned. Yeah? So this example built. And so here is sort of the central vertex, and the blue cube is not part of the polyhedron. It's just there for reference so that you can describe it. The yellow bars are the edges. Yes, so the white bars, the white things are the vertices, yellow edges. So let me trace the square face for you. So I take this as a central vertex, and here is my yellow square. And on this edge sits another yellow square. And now I have to go up. Up, over here, and then down. So on this edge sits another square. Let's see if I can actually figure that out. Here, here, here. So there is a way of actually going around, so after 6 steps go. So Gabo 1, and I suppose to start. So this is a very nice picture. And here are some more pictures of this structure. Then there are also 3 very large families of chiral polyhedra that have helical faces. And the helices can be over triangles, for example. Let's see the first more pictures coming. So helices can be over triangles, 3 coming together at each vertex. The helices can be over squares, 3 coming together at each vertex. And the helices can be over triangles, 4 coming together at each vertex. So there are these 3 very large families. And again, in these large families, there are 2 exceptional values, 2 exceptional polyhedra. And one of them is, both are regular polyhedra, again, because certain positions somehow become special. And let me show you an example. So here again, built by Daniel, who is there. And this has helical faces. And sort of the helix is sort of here, sitting here. The picture is taken in the direction of the helix. And so we have helical faces over triangles, and 3 at a vertex. Here are 4 more views of this object. Here is another one that has helical faces over squares, 3 at each vertex. And here are more views. So a few words about these chiral polyhedra. Some have really stunning properties. If you do a classification by congruence, then there are 2 integral parameters in the finite phase space, or 2 real parameters in the infinite phase space. And it is essentially true that if you, for the finite phase polyhedra, if you wiggle, well, I should say one more thing. If you do a classification by similarity, then you have a rational parameter. So if you wiggle the rational number just a tiny bit, then the icosahedra, then the figure becomes non-isomorphic. So it's a very, very strong discontinuity, very counterintuitive, I think. And these structures are combinatorially isolated, so many, many. And the finite phase polyhedra are actually combinatorially regular, and that was proved by Daniel Plesser and Asia Weiss, both in the audience. And this changes completely for the helix phase polyhedra. Those you can actually move continuously into regular polyhedra. So the geometrically chiral helix phase polyhedra are isomorphic to geometrically regular polyhedra, and you can actually move them into geometrically regular polyhedra. So it's a very rich story, and that concludes one more minute. That concludes the story about the chiral polyhedra. So there are infinitely many chiral polyhedra. And now you can look at structures that have lots of interesting properties in common with your polyhedra. For example, one place where you could actually change everything is to allow more polygons on an edge. Polyhedron had just 2 polygons on an edge. And so, for example, this is a local picture of something that has actually, how many was that? 6 faces on an edge. It takes a little bit of time to go to it, and there's a notion of a regular polygonal complex. And with Daniel Plesser, I've been able to classify all the regular polygonal complexes too. So even if you go away from the parameter 2, then you can classify. And I think this is the perfect time. Yeah, more pictures coming out, I think. Right. Thank you.
Thank you very much for this lecture. Embracing.
Oh, that's so good.
Thank you very much. This lecture embracing so many beautiful ideas on geometric symmetry. Before starting the discussion, I would like to ask everybody not to leave this room, because our organizer, Kristóf Fenyvesi, will have an announcement for all of us. And now it's time for the discussion. Please put your questions or remarks.
I hope, although maybe there is already completed the international tables for crystallography in these polyhedrals. Is it same so done? Full complete set of these.
Yeah, we have them fully classified. They're all classified.
They are fully classified,
Yeah.
but it corresponds to some extent to the tapes made by a good friend of mine, Theo Hahn, and so on.
The symmetry groups, many of these infinite structures are actually crystallographic groups.
Are there also other groups, not only
Crystallographic?
No, yes.
No, that's sort of implied by the discreteness assumption.
But are there three-dimensional objects, or higher dimensional?
Yeah, also higher dimensional. Some of it you can look at.
Thank you.
That's it.
Next question, please.
It would be nice to see the classification of the groups which preserve this structure.
Yeah.
See the structure of the groups, orders, and so on.
Yeah, we have quite a bit of results in.
That's one thing. Another thing is how to extend this to higher dimensions.
Yeah, that's more difficult. There are some results by Peter McMahon, but they are more special. For example, there is classification of regular, so-called regular polytopes of full rank. So, for example, there's a notion of a realization of an abstract polytope, which you would call a geometric polytope, and you can actually classify all the regular polytopes that live in n-dimensional Euclidean space and have rank n. Yeah, so all the finite rank n geometrically regular polytopes in n dimensions. So there is a notion, there's a problem There's a rank, combinatorial rank of the structure, and there's a geometric rank of the structure. And if the ranks are the same, then you can actually classify the finite ranks.
Only a short remark, please. I can. That, as Egon mentioned, this is also related with non-Euclidean geometries. You are invited. Egon will have also a presentation there. Thank you. Thank you.
Here you are.
Thank you very much. I enjoyed very much your presentation, and we learned very much about the classification, new kind of classification of polytopes. But I would like, with my question, go behind your presentation for the future or for future papers. Emil mentioned that you are going behind the Euclidean geometries, and this is my main question. So this classification of polyhedra is based on parallel edges, parallel faces of polytopes, but parallels are ambiguous in non-Euclidean geometries. Non-Euclidean geometries get an importance, for example, in physics in strong gravitational fields, and there is a question how, for example, crystal cells grow in a strong gravitational field. So what can we tell? What can you tell about what happens in such spaces?
In hyperbolic spaces, it would be very nice to do this classification also in hyperbolic space. There are few results. For example, the Petrie-Coxeter polyhedra have been sort of generalized to hyperbolic space. There's work by Asia Weiss and Lusich? I forgot what it's Lusich. And also by Garner on analogs of the Petrie-Coxeter polyhedra in hyperbolic 3 space. But sort of the skewness of these skeletal polyhedra have not been studied. That would be a very interesting question to investigate. But that seems to be very difficult. This is already difficult, especially if you go to chirality.
You sure?
Well, first, it's really very nice classification. My question, just terminological. You use the word petridul, this way. But there are also some people who use the same term for other things. It is if you take a map, just graph and put it on sphere, So we have the vertices, edges, and faces. Yeah. So if you just replace faces by edges, and duality will be, you change the genus, so it will be not the same. It's, some people, me also, use word petridul for this. So we should somehow share the term, So there's another concept. It is not Euclidean. So just exchange of edges into faces, because you can see vertices, edges, and faces just as orbits over reflection. So it's also it's some other way. Perhaps also in this way there are some classification. I don't know.
Yeah, I don't know. I don't know who actually sort of invented the term. It's not my term. I think I don't know if it's already in Coxeter Moser. I'm not 100% sure in this book. But it, in any case, has been around for some time. But I'd like to hear more of what you have to say.
I have just one comment to Michel's comment. If you have this polytope in the sense of Egon, then every edge is shared by 2 polygons. So you can forget about this geometric realization, but you can plug in for every polygon. You can create a map. And then the definition of the Petri dual for the map, it commutes actually. So if he is using the Petri dual in his sense, then, and if we use this operation of putting cells, membranes, to each polygon, then these two operations commute. So
It's the same.
it's basically the same, yes.
Yeah.
It's basically the same.
Yeah, same. So there's an abstract polyhedral underlying it. Same.
Yeah, it's just psychological problem that he's not using membranes. So the polygons are just cycles,
It is the same.
boundaries, not cells.
Referring to my first question, I would like to make sure for me at least. So you said there are three-dimensional, higher dimensional groups, symmetry groups. Are they really space groups with the translational symmetry, or there is no translational?
Or then yes, in these cases.
So if three dimensions, they should be the same. They should be the same.
They are crystallographic groups. Yeah, they are.
And the higher.
It also depends on the discreteness. If you use a discreteness assumption, then again they're crystallographic groups. So Bieberbach theory.
Thank you.
Thank you very much again for this lecture, and also I thank you both lecturers for these fruitful lectures. And now the holding session is over.